Hi everyone, I hope you're okay, and I hope that the videos will keep uploading and helping you out. This is the 11th video, guys, and it's the last video as promised. I'm tackling questions on rates of reactions. Please note that, guys, the other videos are already uploaded. You can just click the link on the description below. It will take you to the playlist that has all the videos, and the other playlist is for those who want to learn rates of reactions from scratch. And most importantly, guys, all of these questions that I'm answering are all extracted from past exam papers. And it's very important for you to know how to tackle such questions, since it will give you an edge whenever you write your exam. So please do share the video to your peers so that they may have the same edge as you. Okay, the apparatus below is used to investigate one of the factors that affects the rate of decomposition of hydrogen peroxide. The balanced equation of the reaction is given below. This is our hydrogen peroxide, which will definitely decompose to water and oxygen. Two experiments are conducted. The reaction conditions are as follows. For experiment 1, you only have 50 cubic centimeters of hydrogen peroxide, which is allowed to decompose at 30 degrees Celsius. For experiment 2, we have the same amount, which is 50 cubic centimeters of hydrogen peroxide that decomposes at 30 degrees Celsius, but now it's in the presence of copper oxide. This copper oxide of ours acts as a catalyst, and the function of a catalyst, guys, is to lower the activation energy of a chemical reaction, and once the activation energy is lowered, our rate of reaction will be higher. Are you together? Or you can simply say the rate of completion for the reaction will simply be faster. We have both experiments which are indicated there. We have our conical flask. Inside the flask we have hydrogen peroxide, and obviously the syringe, guys, is used to collect the gas. Are you together? For the fact that you don't see bubbles over there, that means the gas is collected through the graduated syringe. Are you together? And obviously in experiment 2 we do have our copper oxide powder, which is a catalyst, and it obviously speeds up the reaction. We are told that the reaction of the investigation are summarized in the table below. Experiment 1 produces 0.4 decimeter cubed of oxygen, same as experiment 2, but the only difference is that for experiment 2 you just take less time to produce the same amount of volume of our gas. Okay, for this investigation, was write down the function of a graduated syringe. It just collects the gas from the conical flask, and then the copper 2 oxide, it acts as it is a catalyst actually. Are you together? It is a catalyst, a positive catalyst. How will you know when the reaction is completed? Remember that, guys, the function of a graduated syringe is to collect the gas inside the syringe. Né? If the volume of the gas is no longer increasing, it simply means my reaction has reached completion. Are you together? Okay, write down the independent variable for the reaction. The investigation, guys, would have been, how does an addition of a catalyst affect the rate of reaction? Are you together? So it simply means that our catalyst would have been our independent variable, and the rate of reaction is our dependent variable. Yeah? So in this case, our independent variable is an addition of a catalyst. Are you together? The addition of a catalyst is our independent variable. Then now we must use collision theory to fully explain the difference in reaction rates of experiment 1 and 2. In experiment 2, guys, we'll simply have a higher rate of reaction. Why is that? Because whenever we introduce a catalyst, are you together? A catalyst will lower the activation energy of this chemical reaction. Are you together? And whenever we lower the activation energy, it simply means that the difference between average kinetic energy as well as activation energy will be higher. Are you together, guys? So that's whenever the average kinetic energy is higher, we'll have more effective collisions, and that will result in a higher rate of reaction. Yeah? Okay, an addition of a catalyst, point number one, lowers the activation energy of the reaction. And number two, when the activation energy is lowered, that means the difference between average kinetic energy and the activation energy will be higher. Are you together? Remember that, guys, for us to have effective collisions, this guy should be always greater than this. Let's say this was 5 and that was 10. If it is lowered now, that means this will be 2 and this will still remain 10. So the difference between these two will be greater than the difference between those two there. Are you together? So the addition of a catalyst, it makes the difference between kinetic energy and activation energy to be higher. And that's why we'll end up having more effective collisions, and hence the rate of reaction will be higher. And then now we are told that the graphs below show the changes in potential energy during the decomposition of hydrogen peroxide. Let me rewrite the reaction. That's water and oxygen. If I put a 2 there and a 2 there, that's balanced. Okay, first question, is energy absorbed or released? Energy, guys, is always absorbed in an endothermic reaction, and energy is always released in an exothermic reaction. How do I know whether I have an endothermic reaction or an exothermic reaction? If my enthalpy is positive, I have endothermic reaction. But if my enthalpy is negative, I have exothermic reaction. Are you together? How do I calculate enthalpy? It's just the potential energy of products minus the one of reactants. In this case, we can see that the product is below the reactants, which simply means that our enthalpy is going to be less than 0. That means I have an exothermic reaction, and I know that in an exothermic reaction, heat is always released. So heat will be released, guys, in this question. And the reason behind that is because we have an exothermic reaction. Which one of the curves, A or B, represents experiment 2? Experiment 2 will be represented by B. Why? Because it has a lower activated complex. Remember that, guys, the function of a catalyst is to lower the activation energy. Are you together? And if you lower activation energy, obviously activated complex should also be lower. And then now we must calculate the rates in moles per cubic decimeters at which 50 cubic centimeters of hydrogen of hydrogen peroxide decomposes in experiment 2. Assume that 1 mole of gas occupies a volume of 25 cubic decimeters at 30 degrees. We were given the volume that was collected, guys, in experiment 2. The volume is 0.4 and the time is 5.8 minutes. So I know that the volume is 0.4 cubic decimeters and it took 5.8 minutes. Okay, they want us to calculate the rate of decomposition. Firstly, we must know how many moles of my hydrogen peroxide were decomposed. Are you together? And how can I do that? I must first find the number of moles of the oxygen which was formed. Number of moles of the oxygen will be equal to the volume of my oxygen divided by the molar volume. That's 0.4 all over 25. 0.4 over 25. This will give me 0.016 moles. All right, together. That's the total number of moles which was formed in experiment 2. But I'm not necessarily concerned about the number of moles which were formed. Ne? I want to know how many number of moles of hydrogen peroxide that were decomposed. I know that 2 moles of hydrogen peroxide will give me 1 mole of oxygen altogether. But now I did not form 1 mole of oxygen, I formed 0.016 moles of oxygen. I want to know how many of the hydrogen peroxide will I form. I'll just cross multiply. Whenever I cross multiply, I'm focusing on the stoichiometric coefficients. Ne? That's 1 multiplied by x, that's x. 2 times 0.016, I'll simply get 0.032. But remember that, guys, x represents the number of moles of my hydrogen peroxide which was formed. That's 0.032 moles altogether. But I want to calculate the rate of decomposition of hydrogen peroxide. Now, since I know how many moles will I use, to form 0.016 moles of oxygen, I can simply calculate the amount of concentration that will be used. So the concentration that will be used will simply be number of moles divided by volume. I'll simply use 0.032 moles, and the volume is 50 cubic centimeters, right? Whenever I'm using this formula, guys, I must always change my volume into cubic decimeters. So 50 divided by 1000, since I wanna convert it to cubic decimeters, will simply give me 0.05. So the concentration is just 0.032 divided by 0.05. 0.032 divided by 0.05. This will simply give me 0.64 moles per cubic decimeter. Now I know the amount of concentration that I will use for me to form that amount of moles of my oxygen. Yeah? So therefore, the rate of reaction is basically equal to the change in concentration all over the change in time. Yeah? Remember that, guys, I was asked to find my rate of reaction in mole per cubic decimeters per minute. Mole per cubic decimeter, that simply means I'm dealing with concentration. I want to find the change in concentration, right? So I know that I'll simply use 0.64 of my concentration, and the amount of time, that's 5.8 minutes. So this will basically be 0.64 divided by 5.8. That's basically 0.11 mole per cubic decimeter per minute altogether. So this will be the reaction rate of this will be the rate of decomposition, rather, of hydrogen peroxide. That's how, guys, that's how you're supposed to tackle these questions over there. So please, guys, do stay tuned and wait for more videos. Thank you very much.